So, sound check. Can people in the chat hear me? Can you send me a message? There's some delay. Awesome, cool. All right then. Okay, well, let's get started. So first webinar. As you can see, we put some effort into the setup. People on the screen can see all these blinking lights, although they're not blinking in real life. So I'm going to be able to coordinate everything myself, and this is pretty cool, so I hope you guys enjoy it. Also the content, you know, if that's not bad, that would be nice too. All right, so the basics of microservices. I was thinking of just calling it microservices, but then something struck me. So I've been talking to people about microservices just one-on-one, just passing by, and I felt like, well, maybe this isn't really a topic that I'm the most knowledgeable about. I'm not necessarily an expert, I would say. But it did feel from those conversations like I had something useful to add to the conversation. That I would be able to give people something from the knowledge that I do have. So that's why I thought, you know, I'm just going to say basics of microservices. I'm not going to go too high and too ambitious. But at the same time, looking at the content, it's really about software design. It's not just about microservices. So most of these talks start with some idea of what is a microservice. And I'm not going to do that. So giving myself a little picture-in-picture. See, look at all the fancy features. I'm not going to give you a definition because I think it'll become clear naturally. And I also think aiming this at mostly developers is going to mean that people will have some rough idea of what that means. So I don't think I need to spend too much time on that. I am, however, going to say don't do X. There's some things that I'm going to be saying that are just going to limit what, in my opinion, would be good microservice architecture. So it'll be easier to fill in the blanks, I hope, by not being too restrictive and saying you must do X, but instead don't do X, and it'll leave more room for creativity. So before I go any further, I'm going to regularly have a look at the chat on YouTube. So if you guys have questions, make sure that you post them. I'll try to not forget to have a look and see, and then incorporate that. Right, so next up, my opening position. It's like a hypothesis or something. It's my opinion that as an industry, we are too eager to distribute our applications. And by distribute, I mean anything where you need some type of IPC, inter-process communication, to talk to another component of your application. So that might be over the web, over a socket somehow. That, to me, qualifies as distributed. And the reason for that is those two processes don't share like a memory model or a garbage collector or function call mechanisms. So that would qualify, in my opinion, as distributed. And by saying we are too eager to do so, well, that is just my anecdotal observation that this choice seems to be almost like a starting off or a jumping off point in many projects, where it's like, oh, we will probably need microservices, or we'll probably benefit from such a setup. And as a starting position, it has some downsides, which we'll get to. So I think there's just an eagerness to do that that might not be useful or necessary. So distributed computing. I think it's safe to say this is not a place you want to go. And instead of trying to convince you myself or to argue that, I'm going to appeal to authority. Joe Armstrong.
Another thing we have to deal with failures. Computer systems fail. They're just going to fail. We have to deal with it. We can't ignore it. And this is to handle failures. We need to go into territory that is unusual. To handle failures, you need 2 computers. You might need 10 computers or 50 computers. You can't handle failures on 1 computer. If you've got a program executing on one computer and it fails, you're screwed. You need 2 computers, or 100 computers. If you replicate something over 100 computers, and the chance of one of them failing is 1 in 1,000, then the chance of all 100 failing at the same time is 1 in 1,000 raised to the power of 100. So you can make systems that are almost incredibly reliable, provided you can replicate things and keep them independent. But in order to do that, you need to understand distributed programming and parallel programming and concurrent programming. You see, you can't, this leads you into this territory. If you're running programs on 2 machines, you are writing distributed programs. They run at the same time. That means you're writing concurrent programs. So you need to understand this. This leads you into territory. This is places you don't want to go. So it's quite easy to make things that are not fault tolerant and not scalable. But if you want to make things that are fault tolerant and scalable, you need to go into this strange territory.
Joe Armstrong, he's no longer with us. I think he is mostly known for his the creation of what does Elixir run on? What's the platform? The open communications platform. Somebody. Erlang. Jeez, yeah, Erlang. So the maker of Erlang, one of the few languages built on the premise that you will write a distributed program. So a lot of the distributed programming was built into the language. And he wrote a lot of good papers, white papers, on how to do error handling, distributed error handling. So if you don't know this guy, I would say, there it is in the chat, Erlang. If you don't know who this guy is, I would definitely look at his work. So despite all these points that distributed programming, parallel, concurrent programming is complexity that you would rather avoid, still it happens so often that we choose to do this. And don't get me wrong, to a degree you can't avoid it because we write client-server applications, right? So there's a part of the application that runs on the client, there's a part that runs on the server, and then there's also the database. So even in the most basic 3-tiered architecture, you're writing a distributed program. But to the degree possible, you want to limit that. And so what we often do with microservices or service-oriented architecture is we take the backend block, the web application, and we split that up even further. So why does this happen? I don't think it can be explained by just ignorance. What's the psychology? Well, I have my own theory. Like I'm not a researcher. I don't have any evidence to prove this. But I think web development can get pretty boring pretty fast. I don't think the work that we do building interfaces for data entry, which is what often web applications are, is necessarily the most challenging endeavor. So one of my hypotheses is that I think people just want the challenge. They want to build something that is a bit more sophisticated than that basic 3-tiered architecture. I think that explains a lot of technology choices where it's, some people call it resume-driven development, where there's this new technology, you want to try it out because you want to develop your skills, you want to learn. And I think that explains a lot of what we see. So, right. There's this. There's some hype and desire to solve complex problems. I think that's what's really driving this. Some of the hype also, coming from people that don't actually write code, still think, oh, if we do microservices, that sort of legitimizes our budget and the fact that we're building custom software. Those types of attitudes, I think I see a lot. Although it's hard to admit that, to get anybody to admit that, but that's my suspicion. So, but then why am I saying don't do it? Don't distribute applications. Or if you do it well. What can actually go wrong in the pursuit of scalability and fault tolerance? To quote Joe Armstrong, that's why you want to run things on multiple computers. It's scalability and fault tolerance. And we often don't get those two things, even the main benefits. So I think primarily, the reason you don't want to do it is things get really, really slow, really fast if you do it wrong. So that's the disclaimer at the end. It's just like you can do it right, and then you won't have this problem. But very often, you get it wrong. And before I explain exactly what the design decision is that makes this go wrong, I want to show you this picture that I used to show a lot of students when I was still a teacher at a development boot camp. is this picture tries to visualize latency over the network compared to direct memory access and accessing things from a disk. So every blue box is this many black boxes, as you see in the bottom left, and then equally every green box is this number of blue boxes that you see at the bottom of the second column, and so forth. So if you look at this list, you'll see that one of the fastest things you could do, or perhaps the fastest thing, is reference memory that is in the CPU cache, or reference data that is in the CPU cache. So that's half a nanosecond. That's incredibly fast. And then pretty soon, as you go up, you'll see that a main memory reference, that's the top blue block, that's 100 nanoseconds. That's reading or referencing main memory on the same computer. Now, if you go several orders of magnitude up, this is the biggest example, which is the largest set of red boxes. That's the time it takes for a packet to go round trip from California to the Netherlands. That's 150 milliseconds. So when you look at Chrome DevTools or something, you see latency in the order of hundreds of milliseconds. Compare that to how fast it will be to just read it from local. So this is why, obviously, caching of CSS and JavaScript assets gives us enormous improvements in performance, just because that load time, that latency, you don't have to pay it more than once, ideally. So too long didn't read, I/O is slow. So this is why things get slow. But that's just an observation. We'll talk about the design decisions that lead to better latency and to better performance soon. And then there's the other aspect of what can go wrong when you do microservices architecture incorrectly, or according to me. So what can go bad in such a project is that there will be a resistance to change. What I mean by that is, imagine you refactor a code base and you have a very big class if you're doing OOP, which I think most of us do, and you want to split it into two. That's pretty easy to do locally. You just refactor the code and you deploy it as a single application. There's no big deal, no big infrastructure changes required. If I have to merge or split services, that's much harder. It takes more effort to do that. So we tend to not do that. So the initial setup, the initial decomposition of services is kind of binding us, or at least making disincentivizing change in the future. So we better get that right. So this would argue for starting off as a monolith and then splitting it up once you're confident that the decomposition that you chose was in fact the right one. So that's something that you could do to tackle this mistake. And in general, I would say that resistance to change also comes from a lot of the process involved. Like, you have to arrange changes in the architecture with other teams most of the time. And that takes a process that you can't refactor people, unfortunately. So there's going to be a limit to what you can do there. So yeah, so now I'm making it personal. Like, if you recognize any of these points, then you've probably seen such bad architecture. And I'm not really, I wouldn't normally say, oh, that's bad, good, and be that, only, I don't deal in absolutes, generally speaking, but I think since I'm not addressing anybody personally, I can get away with this. So I will say that architecture where you get these, you pay this price of slow performance, resistance to change, they're just bad. And that's not any individual person's fault. It's just that these mistakes happen. And such awareness is what I'm trying to get at with this presentation. So, now the practical advice, I hope. Let me see, any questions in the meantime? Only sit deals in absolute. Yeah, I had that in my mind, that quote. Decided not to say it, but thanks, Brent. So, independence or decoupling. Related terminology, I would say that the same design decisions that you make in the small when you're talking about single application are still relevant when you do it at scale across multiple services. So what that would look like is to have services that can change independently. one of the things that I like to say is things that can change independently can also change simultaneously. So if you have things that can change independently, you can have two teams working on those separate parts at the same time, and they should be able to deploy independently. So that's one of the benefits that you get from that. Now, the type of independence that you can get with a pretty simple switch of technologies or addition of technologies is to choose message dispatching or message queues over remote procedure calls. So when I say remote procedure call, if you're not familiar with the concept, it's like calling a function except it's remote. It's on a different machine. And by doing that, you're kind of coupling yourself to the fact that that machine exists. So you can't call a place you don't know. So you have to kind of bind yourself and say, okay, I'm calling this particular service. So these services are now aware of each other, or at least the caller is aware of the callee. And most of the time, or very often, you also care about the response. So if it's a REST API, very often you do a GET or a POST, you care about what comes back. So it's not just the coupling of the fact that I know that such a thing exists, it's also a functional dependence. Without the data coming back, I can't work. So queues are a solution to that problem. But not in and of themselves, because you could recreate remote procedure call over a message queue. I could send a message saying find by ID and then wait for a message to come back at some point in the future saying, oh, this is the data. Now all I've done is kind of taken this technology, put it in the middle, and said that it's decoupled, but it's really not. Because still you have this functional dependence that if that data doesn't come back, something will time out or something will hang indefinitely. So it's not really the solution in and of itself, but it does help. So when you're talking about functional dependence, very often, let's say you have a service which is the owner of a certain set of data, of an entity type, let's say. You need that data in order to do your work. And I'm saying, well, don't call it then. Yeah, but if I need the data, I need to somehow have access to it. Well, you could design your system in such a way that if I am the service that owns a piece of data, let's say user profile data, and a user updates their profile, I'll just dispatch a message saying user updated profile. And everybody listening to that message type or to that queue will then take that data and store it locally. They now own that data. What I'm just describing is eventual consistency. Because now there's no synchronous dependency or not dependency, there's no synchronous transactionality between the origin service that owns the data, let's say that's the single source of truth. There's this messaging queue in between that will take X amount of milliseconds before it updates every other service that cares about it. So that's eventual consistency. This is not, again, like Joe Armstrong said, this is not necessarily simple. Reasoning about these types of systems like, can I call service A, update my profile, and then immediately after call system B and expect the updated profile to be there? No. Unless you start doing things like global transaction IDs to make sure that both services have seen the same version of the data before. Like you can do it, but it's not simple. So I wouldn't say that's like an easy thing that you can get into to solve those problems. You don't have those problems when it's a single service. So another solution would be to, instead of duplicating data, is to say share data, but instead I'm going to use a blob store, and I'm going to do content addressable data, which is basically I'm taking a bit of, like a set of bytes, I'm hashing it, and then part of the name of that data is the hash. So that means that whenever I have the hash, I can fetch the data, which means that two services can communicate by saying, here is a hash, and then the other service fetches the data whenever it needs it. And then when in my previous example of the user profile data, if there is an update, I just send the hash. Say, hey, the user updated their profile, I'll send a hash. If you actually need it, fetch it from S3. Something like a blob store that's an immutable, or you should treat it, in most cases, as an immutable data store. So that way you can actually share a database, because a blob store is just a database. You can share a database, that's fine. It's just it needs to have this version semantics. You need to be able to go back and say, what was the data at X point in time, or at X version? So, like I said before, technical decoupling is not enough. You can't just plug in a message queue. Functional independence is a requirement to get all the benefits. So this is, like if you go and look at videos online about services, just service architecture, microservices in particular, that one of the most common tips is that each service should be able to handle a user request on its own. I think it's a good guideline. There are scenarios I can imagine where certain things, like for example in an e-commerce application, the stock of a particular product, you want that to be transactional for sure. Like you don't want two people to order at the same time when there's only one product left, because bad user experience, there's all kinds of consequences. So there's a reason, there are reasons to think where, okay, the service where the stock of each product is managed is going to be a coupling point between all kinds of different user interfaces, and all these different user interfaces, these services, are going to all depend on this singular service. So there's some scenarios where I can imagine yet you wouldn't have each individual service be end-to-end responsible for a user request, but most of the time this is a very good guideline. And then there's the prefix micro, which I think is very misleading. Because micro kind of tends to suggest you want as minimal functionality, or you want the smallest possible service unit. But then you get services that have so little logic that as a testing unit, as a subject under test, they have very little value. I mean, I've heard this so often, and legitimately, like I understand why people say it, that like there's no point in integration testing a single service in this case, like because on its own it doesn't do anything, or very rarely anything. I'll just do the unit test and check the logic. But as a unit, as a service, it doesn't do that much. And I get that. But that maybe is already a signal that you've maybe taken something that isn't like a functional independent unit, but you've taken a very even more granular unit of logic, and you've dedicated a service to it. This is known, as I described in the previous example with the user profile service. That's an entity service. The name of entity service is the name of an anti-pattern. So this is one thing that's more of a historical perspective on microservices, where I think companies, if you look, if you Google microservices or search for it on YouTube, you'll find talks by people at Netflix, at Facebook, showing you the lessons learned. A lot of the things that I'm saying now, you'll get from those videos as well. And I don't think it's a coincidence that Netflix and Facebook have this experience and also had the need or desire to choose microservices as an architecture, or an architecture that they call microservices. I think it's not a coincidence because they're huge. There's a lot of people working there. And they have to work on something that from the outside looks like a single product. But in order for those people to work on the same thing at the same time, as I said before, things that can change independently can change simultaneously. So that means for this many teams to collaborate on a single product, they need these hard boundaries. They need these almost fixed APIs, or at least they need to honor their APIs because they know other people will depend on them. They have to honor this. They have to publish public APIs and say, okay, this part of our application won't change. Because as long as that doesn't change, other people don't have to change with us. All right. So, systems should not look like object orientation in the large. The types of design decisions that you make inside of a single application, passing objects around that have state that travels along with them, that's not the type of application that you want to write when you're distributing the application. Does anybody know Smokey the Bear? No? Wow, okay. So I grew up with American television, and Smokey the Bear was a spokesperson for God knows what, but he would always say, only you can prevent forest fires. was like a public service announcement saying, yeah, okay, so we are the people that start forest fires. You just got to not throw your cigarette out the window. You can't see the... Oh, right, look at that. Oh, there you go. So yeah, only we as developers, as software designers, which is what developers also are, even if they're not very aware of it, the only way that we can really solve this problem is by preventing it before it starts. Now I'm going to show you a quote, or I'm citing a pretty old book, dated 2002. And I'm going to read it out loud because that's easier. There is a recurring presentation that I used to see 2 or 3 times a year. This is Martin Fowler, by the way, during design reviews. Proudly, the system architect of a new object-oriented system lays out his plan for a new distributed object system. Distributed object, keep that in mind. Let's pretend it's some kind of ordering system. He shows me a design with separate remote objects for customers, orders, products, and deliveries. Each one is a separate component that can be placed on a separate processing node. I ask, why do you do this? Performance, of course, the architect replies, looking at me a little oddly. We can run each component on a separate box. If one component gets too busy and we add extra boxes for it so we can load balance our application. The look is now curious, as if he wonders if I really know anything about real distributed objects stuff at all. So this book is not ancient, but it's not very new. And I think distributed objects, when he talks about it, he's talking about things like Corba, which I don't know if anybody has had the pleasure of working with that. Oh, look, awesome. So I can't actually speak for experience, except that I have worked with Java RMI, which again is remote method invocation. Like I said, remote procedure call. I think it's pretty similar, except method is obviously an object-oriented term. Those technologies have lost out. They're no longer with us. Well, for new projects, not so much. And there's good reason for that. It's just that you can't pretend that an object is on the same machine when it's okay, so, where did you, yeah, I hope you guys didn't miss too much. I'm not going to repeat everything I read. So, you missed all the good stuff. I'm going to show you another video clip, which hopefully explains a little bit with the analogy that I just made about object orientation in the large.
And this is where I think we really run into trouble. This is where the problem is, right? What does that look like? It looks like object-oriented programming, right? All these objects are connected and they send stuff to each other and whatever. And it's possible, right? It's possible, but that this system built out of all these processes is exactly like objects at scale. Right? Every process is like an object and it's stateful and it sends things over to other guys and then they change and the whole thing is really exciting. Because service is an arbitrary notion. What does it mean to be a service? You know, you send me stuff and I do stuff. I mean, one thing that's sort of telling is there aren't a lot of verbs, which is kind of good. But you know, all the services are still nouns. The fact that they don't have a lot of operations is helpful about saying, well, maybe they're not like objects, but there's nothing stopping them from being objects. So that is crossed out, right? Yeah, so in what way is this not object orientation? How do we keep it from being object orientation in the large? Because if we've spent all this time doing functional programming in the small, only to build object-oriented programming in the large, then our system in the large is still going to have the negative attributes of object orientation.
Hello. Okay, so yeah, so I can see sound bars on my monitor, so probably you guys can hear me now. What I'm trying to say here is that design is just the second problem. You choose distribution, you do so at your own peril, but we assume that you then also know how to design it properly. And as I said before, there's a name an anti-pattern, it's entity service. And if you have services where the name of the service is a noun, that's potentially a problem. So something like user profile service, right? That tells me, okay, you're responsible for an entity, a piece of data. That means other people will depend on you. And especially something that has user in the name, I assume that almost every service has to do something with users. Right, so chances are there's going to be multiple in-calls to that service, and multiple servers are going to be dependent on it. So that's a problem. Nouns in service names are something to check out. Doesn't necessarily mean it's bad, but it's something to check out. Instead of having nouns as service names, you might want to choose a subdomain as a boundary for a service. And by subdomain, you can think of like an area of business, for example. So if you have an e-commerce application, again, you could think of something like fulfillment. It's not, yeah. It tells me something about the business area where this functionality belongs. And I can imagine that fulfillment service has its own user interface. Right? You may have like a single sign-on on top of it, but the service has its own user interface, own UI, hopefully the same theming, and it looks somewhat like the same product, but it doesn't have to be. And you could have ordering, not order service, because order says I'm responsible for data. Ordering tells me, okay, this is where ordering happened. So that would be a better approach to the decomposition into services. And if you're not familiar with domain-driven design, that's what the 3 Ds stand for. domain-driven design and microservices are a perfect match. Because in domain-driven design, you have strategic patterns and tactical patterns. The tactical patterns are more low-level, code-related, and then you have the strategic patterns in domain-driven design, and one of those is the bounded context. And what bounded context really is this is a boundary of, you could say, language, which is, I think, how it's mostly described. Like outside this context, terms might mean different things. It's a boundary of language, which is useful for a team to live within. You'd say a team is responsible, development team is responsible for that bounded context, saying that, okay, we get to decide our own data model. We get to decide what terminology means what. And outside of that, we just have to, that's like the public API layer, we just have to talk to other teams and make sure that we understand each other, but only for that part of the application. So, what do you get if you do systems architecture right? Scalability. Again, it's what Joe Armstrong said. Fault tolerance. Architectural agility. The ability to change your code, your application. If you decouple your services, again, what can change independently can change simultaneously. People can work faster, which agile obviously isn't synonymous with fast. I think that's also a pretty big fallacy. But definitely the flexibility to change is something that you get if you get the initial decomposition right. Again, this is an argument for starting as a monolith and distributing later. Yeah, so independent teams, I already covered this. Like if teams can have their own bounded context, be responsible for that, they have a lot more control within that. As long as they honor the public API and they do like versioned APIs and they give people or other teams like several weeks or months in order to update to the new version, they can then later deprecate it. As long as they work in such a way, they can do whatever the hell they want, right? They can change, they can innovate, do things. Deploy independently. You don't have to wait and say, okay, we gotta coordinate our releases because your change has to be online before my change has to be online, and those things. Do it wrong and you get bad performance. Things slow down. The inability to change. Teams blocking each other's planning. So I don't think any of this is really news to anybody. It's that this blockaging, this independence, the staticness of a bad architecture, we've all experienced it. So how to do it right? So this is more like a summary. Like we've covered these topics. The best way is to just avoid distribution at all. It's like in the first place, like don't distribute your application unless you 100% sure that that's the right thing to do. And this doesn't say anything about things like actor frameworks, like Akka, or like in the case of Erlang, is also like it's an actor-based system. All right, it's on again. Hello. Yeah. It is. So, obviously, that was just a demo of how distributing a wireless audio system is a bad idea. Yeah. All right. So. Again, I think going back is really hard at this point. So I'm just going to hope that the slides were informative enough that you guys could follow the gist of it. So next up, how to do it right. Except that sometimes you may have to duplicate data, or at least share immutable data. That's perfectly fine. It is eventual consistency, which means that you have to be aware that you can't just, expect it to be instant or instantaneous. And you also have to plan for failure, right? Because there is a limit to how much buffering can happen when there's a message queue, right? So there may be instances where if you duplicate data, that they are permanently inconsistent. In which case you need a batch process or something that will recover from that inconsistency and just like redo the synchronization. That's something you have to plan for. Because, Murphy's Law and all those things. So it's just something that you can't take for granted and say, when it goes wrong, we'll fix it. Because when it goes wrong, like you might have this much data and you might have a deadline. Like there's all kinds of reasons why you don't want to wait to address this problem. Yeah, a red flag. If a service needs another service to complete a user request, reconsider the design. It doesn't always mean you have to redesign, but it might. I think it often does. If you see a call graph for a single user request that requires several services in order to complete a service, you might think, well, could it be different? What functionality is that current user request trying to accomplish, right? Is it ordering? Is it trying to order something? That could be one service. Is it re-indexing? It's very rarely a noun and usually a verb. So that was the last slide. So I didn't get many questions, but maybe now is the time. Questions in the chat, questions in the room. Oh. Nothing? That's fine? All right. Do I know an open source example of a good distributed system architecture? Good question. Well, although it doesn't have a message queue, I would say Elasticsearch, or at least the ELK stack. I think you have a good separation of concerns there. Like there's Kibana, which does graphing and all this. There's Logstash, which is just about parsing and formatting and storing data. And there's Elasticsearch for the indexing, full text search, those types of things. Those aren't even though they don't have actual service names. I mean, they have product names, but you could imagine that Elasticsearch is the search service, which isn't. I guess it's a noun, but I mean, it does something. It is a certain activity. So I would say Elasticsearch or the ELK stack would be a good example to the degree that that's open source. And I've seen a couple of examples. We had recently at Worth had talks with a couple of startups. And they were talking about, we're using Kubernetes. And I thought maybe they made those mistakes. Maybe they distributed early on as a sort of like a jumping off point. But then he explained, no, look, it's a dating app. We have a dating app, and the app itself is served from, has an API. There's a web app, there's a website, there's an API that handles the request from the app. And then we have another service for batch jobs, for doing the matching between two profiles, like two users, so you're a match. And that runs once a day. Like that seems like a reasonable decomposition. That's the type of splitting up where like it's really a different concern. It's also a different business area, you could think, although it's a small company. You could imagine that, oh, that's a separate concern. I want at least runtime independence. I want to be able to run and update that matching service without bringing the app offline. And the app doesn't really communicate with the batch service. It just gets a notification like, hey, new match. And then if you choose to have a different mechanism for matching, or you want to do it real time, you just update the matching service, and the app doesn't have to change. How would you decide what's the right moment to transition from a monolith to a microservice architecture? Good question. I think you start noticing at some point that it's too easy for people to screw with each other's code and to cross the boundary. You'll find that if two teams have decided, you know what, we're not going to do microservices, but we're going to do a modular monolith. A modular monolith, it's a single application, but it has all the decomposition that you would apply to a microservice architecture. In which case, if I wanted to, unless I maybe set some rules in my build server, I could screw with the other person's code, right? If for whatever reason you don't think that works out, or there's just some merge conflicts, because that happens when you start messing across the boundaries, you might say, okay, well, you know, we're going to separate it. And then there's also the question of like, this thing deploys super often, or this part of the system has an in-memory cache that is gigabytes large. And if this thing deploys several times a day, and I have to warm up my cache for this component, then running those on the same machine means that several times a day I have to warm up that expensive cache, which is an expensive operation. So then you want deployable independence, because they have different resource consumption. Sound still on? Just had to check. Okay, so speaking to a CIO, they see microservices with excitement and fear. They want standardization to reduce risk and cost, but like agility. How do we help overcome this fear? Well, a lot of reassurance, for one thing. I think at this point, I mentioned one possible solution, which is the modular monolith, right? So you can automate architecture. Like there's ways that you can write automated tests for your architecture. So you can have ways that say, okay, whenever you write or create a class that has the suffix controller in the name, it must implement A, B, C interfaces. It's like a local in-process object-oriented architecture decision, which is tested for every time you push code to a build server. So there's ways that you can enforce a certain separation or a certain set of architecture rules where you're not relying on pure discipline from developers to not cross that boundary, to break public APIs between components. And then you can do monolith development. But then again, you know, you have to kind of be aware that at some point, because of this, like reasons like different resource consumption, you may want to promote or step into the world of a distributed system. And that has to be easy. If you make that really hard on yourself, then it's like, oh, we started off as a monolith, but like moving to microservices is near impossible, so we won't do it. And so the transition has to be, the bar to that has to be lowered. So the way that you could think of doing that is by having, like if you're creating a .NET application or a Java application, like you can have multi-module projects, right? You have multi-module projects which speak to each other only through interfaces. They don't have access to, the only classes that are public are interfaces. And then everything else is either package private or private. So we can't see those things, which means that I can only ever rely on the public interface. And as long as I send data and I don't send objects with state across the board, also something that you can automate, as long as I don't do that, I can take each module and deploy it independently. I can say, and now the interface that you talk to is actually an HTTP client. Right, so you can then, at that point, evolve into microservices. But you have to start off with a hard enough boundary between the modules, between the services, so that transitioning to microservices is easy. And I'm sure there are platforms out there frameworks out there that will let you write your application in such a way that move is invisible to the developer. You just start off sending pure data across interfaces, and if I want to take those two building blocks apart, the only thing that changes is the deployment model and not the application code. So there's ways to do that, and like I would just reassure that this is just a design decision which we're free to change later. Like the change later is inexpensive, in which case I think you should be able to convince somebody that that's possible. And maybe you do that with technology or just the developer discipline, automating design rules, but yeah, that's neither here nor there. Could performance/availability be a main driver to go with microservices from the start? Sure, yeah, absolutely. So I think that the independence that you get from a well-designed distributed system means that for a particular set of user requests, I am independent because I service those from other services. So if they go down, definitely availability is a benefit, right? So I think that's just another term for the most part, for fault tolerance, which is what Joe Armstrong called it. It's like fault tolerance, availability. If you fail, I can still do my thing. I'm independent. And performance, maybe. So you can imagine, like with a lot of stream processing things, you want to be able to horizontally scale. Like if you have an ad serving platform, which I briefly worked on, it's like that you don't guess how many ads you can serve per second. Like you don't want to allocate a server that can handle just this much, because when ads stop serving, you lose a lot of money per second. So you just want to have that flexibility there that, oh, if we have a spike in traffic, I can scale horizontally. So then performance might be a good reason to distribute our application, or at least have like a shared nothing architecture where part of it can scale independently. How should you deal with authentication between the different services? Interesting. Do you mean authentication saying I authenticate that I am service A, or do you mean like user authentication across services? I can answer both questions. Look, I think the first question shouldn't be really a concern. I would use an encrypted transport layer if you're going over the public internet, and if you're not going over the public internet, service authentication really? Like you don't trust your own services? Like what's the point? And over the public internet, you can use something like TLS. The other thing is user authentication, which there's multiple ways you can solve this. Like you can have a shared user service and say, okay, this is the one service where we do have an RPC dependency on the service. You could go that way. But then you have to cache things, right? I would choose the share immutable data option in this case, where you fetch a session saying this user logged in, this is the session ID. And when I fetch it, I know, given the ID, that this session data will not change. It's immutable. So I can store it locally so that the next time the user makes a request to me, I don't have to go fetch the session again. So that would be a way that I would architect it so that there is this single source of truth for the session data, but you can share that data because you do versioning. Yeah, so Robson asked, was it, he meant it the first way, so authentication between services, I am this service. Well, it depends on the trust level. I mean, if you have services being developed by external teams, it goes over the public internet. Yeah, maybe, although even then I would say, like you should need,
Yes, it would be a defense in depth measure.
Defense in?
In depth.
In depth.
Yeah, so it's a second layer defense, I guess. So if one service should only be called by one other service. So imagine one service being compromised, right? Then this service could call all of the other services. And if there's no layer between
Right.
them,
So I get that. So I think in that case, if you have like a single network, virtual LAN, like a resource group in Azure or something, where there's all these things living in the same subnet, they network-wise they can call each other, and you want to limit that, I would say, well, but you're already in such a safe zone that it seems like overkill, because what you get there is you need things like keys that need rotating. Right? That's another layer of complexity that you need to architect for. And I'm saying if you have it and it doesn't slow you down, go for it. But I think probably there's a cost to that, whether it's development time or performance for the call itself. So it's a trade-off. I wouldn't say it's a big benefit, but that's me personally. I'm not a security engineer, so.
So for example, in Carol's project, I've seen it used that there are endpoints on the services that are shared between users and other services. And then it's very important because it's an endpoint that's open to the internet as well. So you can either, there's like two application schemes. One is for the user, the other is for the service. And the service uses a JWT token to get authenticated.
Yeah, but that's kind of similar. Yeah, I guess it's the same thing. It's kind of similar to like mutual TLS, right? You have.
No, yes, exactly.
So you get even though with TLS it's actually encrypted, with JWT it isn't necessarily.
Yeah, and it's on a different layer, right? So
yeah, exactly right. It's at the transport layer, so you don't. It's also an older technology, so I think adopting something like that is probably easier. There's less maturity issues with that technology. So I think I would go that route and have something like a certificate-based authentication.
yeah, right. So yeah, that's actually nicer, although you do have the practical problem of if you want a shared endpoint between, let's say, so for example, it works with Azure Active Directory, so you have this bearer token. So, and then there's one endpoint that works for both. So then you would have to have two authentication schemes. So how do you know it's the service calling that endpoint? So the authentication takes place in the application code itself, and not on the infrastructure level.
Yeah, the question is, do you need that? So the difference is, do you need your application to authenticate the calling service, or can it be done at a lower abstraction level? I don't know. That depends. It depends. I think my tendency, as you can tell probably, to just not do it at all is because I think unless you deal with an external service provider, there's very little point to it. But when you do, then that's a different story, right? And then you can also consider something where if you're considering authentication at that level, you can also think like, should there be a shared sense of which user is performing that action? In which case, you could use your single sign-on technology for that, and you just propagate the session ID or the user ID across that call. In which case, you don't do service authentication, you do user authentication, which might even be more powerful depending on what you want to do with it. So yeah, again, I think it's really it's rare that you really need it. If there's that much distrust that some service might be compromised because it's out of control, it's being developed by a team that we don't really trust, and there's all these reasons. Yeah, then maybe you do it, but it's like it's a last resort. Or yeah, it's a.
Yeah.
The cost benefit I think goes a lot in favor of not doing it.
Yeah. So yeah, in this case, it's just a practical solution to share one endpoint for both external calls by users and also internal calls by your trusted service, right? So this is an endpoint that can be called anonymously as well, but you have to provide either a bearer token from the Azure Active Directory, or you provide this JWT token, which will identify you as a service and will be trusted.
Like a service principal.
I don't know. What's a service principal?
Like the distinction between two calls is only that this token represents a user and this token represents a service.
Yeah, exactly.
I see.
So
Okay.
that
Yeah.
makes it reusable, right? You have one endpoint that's
Sure. Yeah.
callable by an anonymous user,
Right,
but
yeah.
also by a service.
Yeah.
But it needs to have this authentication though, because otherwise you don't know it's a service calling. But
Yeah.
versus anonymous.
Yeah, I mean, a service identity is very often useful to distinguish user calls from calls that happen because the services need to resync, for example. Like if, like we had the example that if two services have an eventual consistency type dependency, that if the data gets out of sync, it might be nice, hypothetically, to have service A say via RPC, okay, this thing, I got a global transaction ID from a user that I didn't recognize, so I'm probably out of sync. I'm going to go fetch the latest version of that. In which case, I'm calling it as a service, not as the user that made a request. In which case, I'm allowed to do more things, right? So sometimes you're allowed to do less as a service, sometimes more. But yeah, so that would make it transparent. Like it doesn't. Your authorization rules are take into account that you might be dealing with a service or a user. Yeah.
But there's another. I'm sorry. Go ahead.
It sounds like you should do a talk, perhaps.
Yeah, we've got the technology.
Yeah. Well,
So
there's another interesting problem that I've seen before is that there's a super much trust between services. So any service can call any endpoint on any other service and change anything, basically. So what do you think about? But obviously that shouldn't be possible, right? You have certain flows that users can follow and that will propagate between services, I guess. But some other things shouldn't be possible. So if you have this domain-driven design, right? So you have a domain. Where do you stop trusting the other team from making the right security calls? You give them full control over calling any endpoint on any service in any circumstance? Or do you want some kind of control, like, hey, look, you can only if you're an admin, you can access the admin functions within our domain. Well, I'm talking about, actually, for example, you could say with each service call, inter-domain service calls, right? You would say, I also need to know what role you're at, so I don't let the, let's say, other team or other domain make the mistake of calling the wrong API endpoint, so I give too much permission to what the user.
but that's the propagation of the user identity, right? So you need.
Yeah.
So you need.
Check it again, inter-domain, I guess. Like there should be a point where you're gonna check it.
What do you mean inter-domain?
Well, if you have like a group of services, right? So you have two domains, one group of service, another group of service, and one group is calling the other one. Do you check again, like, is this user even allowed to make this call?
Well, I mean, okay, so let's pretend we have, so the question is inter-domain communication. How do you make sure that the user making that request is of the right role?
Yes, authorized.
So I think that's also a question sort of addressed by domain-driven design, where if you have a bounded context, and let's say it aligns nicely, which it hardly ever does with the service boundary, you could say that, okay, well, we're going to do this context mapping thing where I don't know anything about you guys, how you do your user roles and your authorization. I just know what I expect. And I expect is owner of particular object ID. I expect that type of authorization. So in part of my API spec, I say this role is required in order for this user action to succeed, which means that the user session or ID that they propagate, I will check against my authorization tables and see, okay, he is the owner of this entity, so he's allowed to do X. But then that domain, that context, that bounded context, owns those rules and gets to update them. Yeah. So Jorge is very excited about the security-related questions, but the depends on depth. Could also. Yeah, your comments are really about the trust boundary. I think if you are dealing with something remote, obviously authentication makes sense. Encryption over the wire, it makes sense. But I think a lot of these things also with the last question can be addressed with user authentication rather than service authentication. Which is at the core a much more necessary functionality than service authentication.
Can't do without.
Usually no, unless you never service users. How do I feel about micro front-end? So I think with functional independence comes also the requirement or the preference to have your own user interface, right? You want to be able to update the UI at your own pace. You don't want a single SPA that's the front end for a whole bunch of services. Because again, that's where the concerns come together. It's in the user interface. And where those concerns come together, you could have something like micro frontends where what you end up seeing is just a composition of all these different published UIs. And there's a lot of ways that you can architect that. I have to admit, I'm not up to speed with what the state of the art is in micro frontends, but I think in principle, it's a very, very solid and good design, because then you can keep that independence. For example, you could have a service that is responsible for the UI that is shared. So people can fetch the latest HTML templates and CSS and JavaScript from a particular endpoint and get notified whenever that changes. And they can wrap as a shell around their own user interface their own things. And then there's not even call propagation. There's not even a proxy needed, because every service maybe has its own subdomain or its own path going through a load balancer that can serve their own UI. So I think that keeps things independent, keeps teams independent without blocking each other. And if you do the right thing, like good rules with regards to CSS, class names, etc., you can say have development teams create their UI, and they hardly even know what it's going to look like. You just follow a certain structure, and you could just say maybe next week people change the CSS, and now all of a sudden the padding is different on all my buttons. You know, it's like you don't want to bake that into your code. Again, that's something that you could automate to make sure that people don't violate. All right, we went a little bit over time, so it's 12 past. I hope you guys enjoyed it. I'm going to wrap up now. Everybody online, thanks a lot for joining. If you guys have feedback, you can comment on the video, post it on Slack if you work at Worth, and see you guys next time. All right. They're applauding. Can you hear them? They're applauding. Yeah.
There are a lot of jokes about the sound.
Yeah.